Well, hey, it's great to be together. And welcome to the February meeting of the Stockton Astronomical Society. We're going to go ahead and get started. I'm Tim Clark, as you guys all know, and some guests coming in. And I see Tom Field, our presenters here. So Tom, welcome.
Thank you.
James Shipnick, good to see you. Paul, Ray, you guys are on Zoom. It's good to have you with us. We'll get started here in just a minute. It's good to see you all survived your trip down the atmospheric river on the Pineapple Express, right? For what it was worth. I got curious what the rainfall amounts to date have been. So I looked up the NOAA website and I found it pretty interesting. I'll share this with you. Northern California has been hit a lot less than Southern California, as you all have heard. Like Sacramento to date is 107% of normal rainfall to date, 107. Stockton's 114. But then you flip over to Southern California, and most of them are over 150%. Some of them over 200%.
You got 2 inches.
Yeah, they deserved it, right? Maybe they won't be begging for our water this coming year. So,
Oh, they will.
yeah. Anyway, I'll pass this around. You guys can take a look at it right after you've signed up for refreshments for the year. Okay, so I'll start the list over here with Mike.
I don't know how to write.
Don't give him a pen, because Mike always brings great refreshments.
Actually, it's just white.
Yeah. Okay, well, with that, I think we can go ahead and introduce our speaker, Eric, and get started with the program, and then we'll just have announcements after that. And so, Eric,
Okay.
take it away.
Okay. Hello, everyone. Our speaker today is Tom Field. He is a pioneer in amateur astronomical spectroscopy. He was a contributing editor at Sky and Telescope magazine for 10 years, and he is the founder of Field Tested Systems and author of the RSpec software, which received the Sky and Telescope Hot Product Award. He promises to demystify the field and open the door for us tonight on how to do easy hands-on science. And if you want to learn more about his software and more about spectroscopy, you can go to his website, www.rspec-astro.com. And I will hand it over to Tom. Give him a round of applause.
A virtual round of applause. Thank you, Eric. And just a reminder to everybody but Eric that it's a lot of work putting these meeting speakers together. He and I initially communicated, Eric, you may have looked in your email earlier today and seen the same thing. It was August of last year that we first started talking. So it is tough stirring up speakers, and I'm really happy to be here. I'm just a normal guy and who knows far less than what people sometimes expect, but I'll prove that during the evening, especially during Q&A. So let me share my screen here. Now, if at any point, because during my presentation, I may go in and out of sharing my screen. If I forget to come back to my PowerPoint, somebody can just jump in and let me know. And again, if you're not seeing that prism there right now, please let me know. So I've been an amateur astronomer for about 25 years. I'll tell you a little bit more about that and how I got into all of this. But the main thing is what can you do? And even if you're not an imager tonight, I think you'll find a lot of foundational information that's helpful in the armchair kinds of reading that we all do. So there we go. What presentation would be complete without this iconic photo, right? The thing is, this is gorgeous, as we all know. We have admired it for many years. But I always wonder about all the other stars that are, not in this area, and, not these nebulosity. What about all these? What are those? And, I sort of feel like they got left out. They all have a story to tell. And my experience was that I didn't know a lot about the life cycles of stars. So, we all are, again, a very overused analogy, but we are all standing on the shoulders of giants, and they've had centuries to accumulate this knowledge that we're now trying to absorb in short periods of time. I'd probably be about out here, maybe somewhere out here. So, but I think it's important to acknowledge that not only have they done amazing things, I don't want to be anywhere in this tower, I assure you. And you'll see, as I said, as we move on, that'll be proven tonight. So the frustration that I think all of us have as amateurs, I know I have, and that is, I wasn't sure, I've never really been sure how to learn more about the field that we love. We're all in it because not just for the pretty. I mean, if you're at this meeting, you're self-selected for enjoying the science. And there's so many ways to learn the science that I struggled for many years, and I felt like I wasn't learning as much as I wanted to. I want to look at some examples tonight of the kinds of science that you can learn from spectra that you can capture. Again, just a couple familiar examples here. If we look at Orion's belt, there are 3 stars in that belt, and they all have their own spectra. And these spectra over here tell us something about where the star is in its life cycle. This is captured, this image, on a DSLR. Unlike most of the images that we see when we're reading online or in magazines, this is something you can do. I've always felt like the magazines, not deliberately, but were a little misleading. And you may have had the same experience I did. When I was much younger, I'd see some photograph of some gorgeous galaxy, and I didn't have a telescope, but I knew I wanted to get me some of that. I figured, okay, I'll get a telescope. And it's only later that we discover that it's not so easy to get those images. And in fact, when I'm in person, I sometimes will ask somebody in the audience to pull out a sky and telescope or astronomy and go to the back, the showpiece section, and find some beautiful faint fuzzy and show it to us, and then read the fine print. And the fine print is always, 20, 30 hours of integration time with some sort of CDK telescope, and, on and on. I'm from Seattle, and I may not get 20 or 30 hours of observing time in a whole summer. The nights are short, and they're often cloudy. So the reason I tell that story is I want to emphasize that unless I point out otherwise, everything I'm showing you tonight are images that were captured in a few seconds. And this is the kind of thing you can even do with a DSLR, and we'll see examples of that. So let's dive a little deeper into Perseus. What do we have here? I'd say it's a boring star field. It's nothing, right? There's a little bit of color here, but, really, there's 3 stars here that I've chosen just to show you how much is in these seemingly boring or uninformative, unexciting star fields. So this is that same star field. You can see the 3, I'm pointing on my screen as if you can see me. You can see those 3 stars on the left, and on the right, you can see the spectra that they produce. Now, I'm going to talk in a few minutes about how we create these, but I wanted to show you the kinds of things that we can do. Because these spectra, if you look, there's some gaps, right? And again, for those of you who know this foundational material, hang in there. We'll move on in a little bit. I just want to get people to a level where we can talk about these things. So these gaps, whether they're gaps or whether they're bright lines, are like fingerprints. Every element has a different spectral fingerprint. So if we look at this one, without getting into the details right now, partly because we don't have time, but partly because, to be honest, I just don't have them. This is a type M star, and we know that from that spectrum. And again, just familiar diagram that we're going to talk about here, but I have a quick story. Some years ago, my wife was using her Garmin, to give you an idea when, and she had a chore to do in a strip mall south of Seattle. She went in, she did what she had to do. When she came out, she told me later she didn't know once she was in the car which way to turn as she left the parking lot because she didn't have a map. And the reason I say that is because without maps, it's really difficult, especially for those of us, if this paradigm has any accuracy, who are visual. So, of course, this down here are the stars in temperature order. There's some stars that are quite cool, type M stars, and then there's some hot stars, and this number, this lettering and that kind of sequence information is historical. But an M star, like the one we were looking at a moment ago, falls here, like where Betelgeuse is. Now, we're not going to get into a lot of details in this, but this is the map that I discovered, and I imagine many of you have, was really key to my beginning to compartmentalize and understand what stars were what and where they were in their life cycle. So this is color temperature down on the bottom, and this is just the brightness of the star intrinsically. So just to point out a couple, here's Vega, here's the sun, and as we go to the left into hotter and harder stars, we've got, you know, a variety of different, there's Spica, for example. So this first star we looked at is this one. I'm going to keep moving. We've got a lot to cover tonight. So what about this thing here? It doesn't have those gaps, but it does have that very bright spot, right? So this is what's called a BE star. Now this, again, remind you, is a DSLR image. This is not a whole bunch of stacked images from some mountaintop. So a BE star is a star that has an emission line, that's that line, from the glowing circumstellar disk. And we can place a BE star, again, on the HR diagram, on this diagram. It's a B star, so it's somewhere up in this area. So now we've, again, visited two different regions on this HR diagram. And the last one here that I want to show you, and then talk a little bit more about it, is this star here that has a lot of bright spots. And those are emission lines from a Wolf-Rayet star. It's a late-stage star that's expanding, and sort of very strong stellar winds are blowing out a lot of the gases. We can see down inside and see a lot of the byproducts of the stellar fusion with you know, various elements that have been consumed and synthesized. So the reason that I feel this drawing is so valuable to all of us, and what I found was, when I first saw a Wolf-Rayet spectrum, to be really honest, I didn't know what a Wolf-Rayet star was. And here's the takeaway phrase: once it's your data, your relationship to the data and to the writing and reading about it that you do is very different. Then when you come out to Wikipedia, you've got skin in the game, right? This is a spectrum that you captured. And you can see here that these Wolf-Rayet stars, we won't read all this, these Wolf-Rayet stars can get very, very hot. And so that would put them on the HR diagram, you know, somewhere over in this region, way up here. So again, the point, and we'll move on here, is that by learning different neighborhoods and how stars in their life cycle move through this chart, it's a foundation that allows us to compartmentalize and remember, which, looking at this audience, many of us, memory is always a thing. So again, the way you capture spectra is with this 1.25" grating. We sell it. It's called a star analyzer. It's about $200. You spend more than that on an eyepiece, I bet. You can attach it to most any instrument. I'm not going to get into a lot of the details here. It can be a video camera, which speaks to how short the exposure time has to be. You know, just a half a second or so on some of the brighter stars. So all those stars, which really don't have a lot of interest to us these days, they just get in the way of other things we're trying to image. Those stars all of a sudden become interesting to us because we can capture their spectra so easily. Now, it doesn't have to be a color camera. It can be a mono camera. And of course, if you've got a filter wheel in your system, you can put the grating in that. So tiny bit of history here. Again, Sir Isaac Newton, split light, white light into colors. We can do the same thing with a prism. We can also reflect light off a finely lined surface and get a rainbow. And again, a DVD or a CD will do that. So Bunsen, some people don't know this. In fact, many people, at least I didn't. Maybe I should stop projecting. So Bunsen invented the Bunsen burner to burn things. and then put them through a prism, put the light through a prism and observe the result. And so he is in some ways the father of spectroscopy. An interesting fact about Bunsen, you may have known all that, but the fact that I learned somewhat recently was that he deliberately didn't patent the Bunsen burner. He said, I want to have this available for humanity for discoveries and for the betterment of our lot. And that's pretty impressive. Of course, if he lived today, he would have had a lot of patents for it, or his employer might have. Kirchhoff, we're not going to get into a lot of detail, except to, in a minute, talk a little bit more about him. So I showed you this a little while ago, that each element has its own fingerprint. And hydrogen, for example, is so common, we actually give these specific wavelengths where we see the fingerprint of hydrogen, a lettered name so that we can talk about it. We'll see a little bit more of that later. We're not going to look at any of the details in this, except, again, to bring my point home, you can see that hydrogen has a very different series of lines when it's burnt than helium, like the helium that you get in a birthday balloon at the supermarket. But there are those lines, hydrogen alpha, that hydrogen beta. What color would you call that? That's sort of, let's call it robin egg blue. So, and we'll be seeing a little bit more about that in a minute. So, just to go back a minute, what does everybody we've looked at, all the astronomers we've looked at so far in this presentation, have in common? It's that they're old white men. And when I started giving these talks some years ago, I wanted to bring in a little diversity. And I just found there was so much amazing work done by non-old white men. Annie Jump-Cannon is a familiar name to many of us. She and her team of what were called computers were prohibited from touching the telescopes at Harvard. And so they ended up basically studying these photographic plates of, you bet, spectra. This isn't a spectrum here, but I gave this show to a club and they asked for the slide and somebody zoomed in on it and they said, I've been studying that star, that's a photometry of a mirror or some star, I don't remember what. So other great names, Priyamvada Nataraja, I think she's at Yale studying hyperactive black holes. Nancy Grace Roman was a big proponent of the Hubble Space Telescope. Elisa Quintana studies black holes and exoplanet. That's studies M stars, cool stars, and the exoplanets that are orbiting them. And Jedediah Eisler is at Dartmouth, and she is also studying black holes. Lots more really interesting people in the field we don't have time to talk to tonight, or talk about even. So enough history, theory, equipment. Thanks for sticking with me on that. What can we actually do? So we take starlight and we put it through a grating. And again, some of the starlight goes straight through, but some of it gets bent into a rainbow, or a spectrum that shows up on our sensor. So what can you do with that? This is a cool slide. It's one of my favorites, this next one. These are separate images taken of different stars. They weren't all captured in the same frame. So, and they're in temperature order. So hot stars, B stars, A stars, all the way down to cool type M stars. So the cool thing about this is it really makes it clear that stars of different types, different temperatures, have very different spectra. They say like 70 or 80% of what we know about stars and their life stories comes from spectroscopy. So even as I said earlier, if you're not capturing spectra yourself, knowing a little bit more about how it's done can really open up. I found when I'm reading articles and they start talking about spectra, I go, oh yeah, I know what they're talking about now. Two quick examples to show you the differences here. These cool stars down at the bottom have these wide bands. You don't see those bands up there, do you? So that's because these cool stars are cool enough that some molecules can survive in their atmosphere. And it doesn't matter their proper noun. They happen to be titanium oxide, but that's all I can tell you about them. So the cool thing is, again, because there's no final exam in a hobby, we get to decide on where we want to explore and what knowledge we don't care to pursue. So the last example on this screen is this region here in the robin egg blue. That's the hydrogen beta line, and you can see it's very dark and broad on these type A stars. And just as a refresher, what are these spectral lines caused by? In the Bohr model of the atom, you have shells, and electrons sometimes jump between shells. And when they jump between in a hydrogen atom between shell 2 and 4, you get this absorption line here. So these stars are too cool. That's why these lines aren't very dark, because, too hot. So a lot of the electrons, they don't stop here. They just keep going. And these stars are too cool. You don't see any hydrogen lines here because the stars just aren't hot enough to pump an appreciable number of electrons up to shell 4 from 2. Okay, so let's just talk really briefly. And that is, sometimes you've already seen this. Sometimes you'll see a spectrum with gaps. Sometimes you'll see them with lines. Notice they are all at the same position. Which you get depends on things we won't talk about tonight. The temperature of the gases that the light went through. This is all what Kirchhoff, Bunsen's buddy we saw on a screen a few minutes ago, talked about. Okay, so let's see what we have here. Oh, there we go. So suppose the Hubble Space Telescope people made a huge mistake and gave me observing time, and I captured a spectrum. And then I saw a little bit of dimming here. And I wrote a paper that said in those words, there was a little bit of dimming in the robin egg blue. You know, that's not science. They would have made a big mistake. So in order to talk about these things quantitatively, we have to do something with this image. And what we do is we plot the intensity of this region. So let's see what that looks like. So this is the intensity axis right here. And you can see this is very high because the star is very bright. That's the starlight that didn't get bent. Some of it goes straight through the grating. And then over here, without getting into a lot of details, we can see that what's barely perceptible as a gap here, a little darkening, really shows up clearly. Now we're doing science. We can measure the depth of that, how far away it is from the star, what color it is, all sorts of things. So this is the kind of thing that we're able to do with amateurs. So my story was I wanted to do this, and I picked up one of those. I don't have one sitting here in the hotel room, but I picked up a star analyzer grating and tried it on my C8 in the backyard in Seattle. It was August. I came in at midnight. My blue jean knees were all grass stained. It was a C8. We're talking Vega. This is in like 2009. And the next morning, I tried to create a graph like this from this image. And this literally is that first image I captured. And I couldn't. I used shareware that was out there. Sometimes shareware can be quite good. In this case, not only was it crashing a lot, but to add insult to injury, all the error messages were in French. So I'm now friends with the author of that software, and she and I have laughed at that story of mine. But I gave up because I wasn't having fun. I told my wife, this is a hobby, and I'm really just angry at this software. It's no fun learning software that isn't well documented, isn't well designed, even by the author's own admission. Valerie, who wrote one of the programs I was using, she said, I'm not a designer of software. That's not my forte. So I end up put the star analyzer in a drawer, and about 2 weeks later, it was still bugging me because I wanted to do this science. So I figured, okay, I'm a programmer. How hard can it be? And so the next weekend, I spent a few hours or a few days, created this little graph from the image at the top. And now 10 or 15,000 hours later, I'm almost done programming. Things go that way. If you're a software developer, you know that. But so I just wanted, I'm not going to get into any details here, but just to show you an example here in Pegasus, and you can see all those stars have unique, interesting spectra. And that's the kind of thing that we can observe here. These, by the way, are done with a more expensive device we'll be talking about in a moment. So I wrote this software for my own use. And I know, especially at this hour, if I go into a full software demo, I'm going to start losing you. And those of you who haven't muted your mics, will be hearing your heads hit the mics as you fall asleep. So I'm not going to do that. But I do want to spend 2 minutes because I think it's important that you see that it's not nearly as hard as one might be afraid it could be. So this is literally the image I got off. It was, you won't believe it, it was a Logitech webcam duct taped to 2 star diagonals because I needed more back focus. And I mean, I got very lucky, to be honest, to capture this image that night. God knows I didn't have the skills to do it. But there's the star, and there is the spectrum from the star. Now, I was using a color camera, but as I mentioned earlier, need not. There could be other stars in this field, but in this case, there weren't. So all one does is just use my software lines, these little sampling lines, and bracket in an area. And now over here, we have that graph. So this peak here is the intensity of that star. And this thing shows up over here. And that, let's just look at this here. That little gap right there shows up as that dip. So now we can do science. So final step, and then we'll go back to the PowerPoint show, is there's lots of little dips in here. There's one maybe over in the robin egg blue. They're hard to see here. I mean, we could zoom in and there's one there, there's one there, you know, but they're hard to see. So what are those and how do we analyze them? And this is, I think, where I felt most intimidated, because I wasn't capable of doing new work, of sort of going, okay, let me just study this and I'll figure out what all these lines are. Most of what we do as amateurs at the beginning and intermediate level is, you know, we know what we're looking for. And so, you know, from various books we'll talk about in a minute, there's samples and there's, you know, forums online. And so you know what you're headed for. So there's no creating new information. There it can be, but I don't want to spend much more time talking about that. But I do want to slide the little Zoom window out of the way so I can get up here and just click here. Built into the software is the periodic table, including the Balmer lines. Where are the absorption lines from hydrogen? I'm not sure I mentioned the word Balmer earlier, but those initial lines that Bunsen discovered were called the hydrogen Balmer lines. And here we can see that the reference lines in my software go right through where there's an absorption line or a dip in the data that I captured. So this is confirmation. It's a little inaccuracy down here, but this is confirmation that we really are observing, you know, data that is revealing the composition of a star. With a C8, 2 miles from Pike Place Market in Seattle in my backyard, knuckle-dragging imager that I was and still am. So we'll leave the screen. The one thing, if you would, in your mind's eye, just sort of remember that. We've got Vega, and we're seeing where the hydrogen Balmer absorption lines would be, because we'll come back to that in a couple of minutes. Okay, so back here, if you can't see the PowerPoint slide, let me know. Sometimes I forget to come back here, and bring the screen up properly for people to see it shared. So there is a gas tube in my office. There's that robin egg emission line from that tube. It's a hydrogen gas tube. So whether it's a gas tube locally or a star that's you know, distant, we can compare the data. Okay, so we also happened to a few years ago, about 10 years ago now, we took this software and we built a little spectrometer for high school and college classrooms. And it's been quite popular. Chemistry teachers love this topic because they're teaching transitions and orbitals and things like that. And so here you can actually show your students in real life or at a star party. You know, you probably wouldn't do this at a dark site, but this is in France, in Marseille, France. Somebody's showing a gas tube spectrum right outside the dorms of the university, it looks like. So, and this is, before we look at M57, this is a topic, you know, when you look at the kinds of spectra that we can observe. And in fact, at some peril of being accused of coming back to something I said I wouldn't come back to, I want to show you the video. Again, happened to be color, need not have been color. This is the video that I made that first night on my telescope with the Logitech camera. You can see it moving around because the seeing was so bad. You know, just watch that star moving around. But this is a really cool screen to use at a star party because it's pretty, it's colorful, it's moving. And when people come over to talk, you can have, you know, some fundamental ideas to talk with them about. And it really turns into a great outreach experience. And you can even do that with schools. As I mentioned earlier, lots of educators, not only astronomy educators, but physics, chemistry, they're all looking for cross-cut, for ideas that cross over interdisciplinary. And this is the kind of topic that brings things to life for their students. So if you were doing this with a small portable telescope, you could, have an evening event at the school. You could do this. The other thing I wanted to mention is urban light pollution just isn't as big a deal for this as it is for visual imaging, because we're not so interested in all the fine gradations that visual imaging requires. We really struggle, of course, to get very dark skies. And with spectroscopy, we're just looking for those dips. Yeah, dark skies help, but you could do this probably at your local high school in spite of the light pollution. So what about our beloved M57? Here we can see that there are just two colors coming out of it. And again, there are ionized oxygen. That's what that 3 means there, Roman numeral 3. It's ionized, that some of the electrons have been pulled out, and hydrogen alpha line. This is an extended object. So with a $200 slitless grating, this is about the only thing that you'll see of any interest that's not a star. When you start looking at extended objects like Jupiter, Saturn, they're too big for a slitless system. So let's talk about slit systems. These are systems that are considerably more expensive and harder to use. Try guiding on a 20-micron slit someday. And furthermore, although there are some DIY 3D printed devices for about half the price you're seeing there, maybe even a little less, $600-800. It's a big step to start out with, initially with the slit spectrometer. So not many people do that. Here with a slit spectrometer, we can see M42. We're seeing, what's interesting is this is, of course, the birthplace of a star, and M57 is a star dying, but we're seeing the same features, hydrogen alpha and oxygen, ionized oxygen. This, of course, is an extended object. So with a slitless grating like my star analyzer, you just wouldn't see any interesting spectra at all. So now this is really cool. This is Uranus at the top and Neptune in mono, done by Torsten Hansen. You can see his name there at the upper right-hand corner. And if you feel like you're drinking from a fire hose, you are, I apologize. I just want to keep moving. We will certainly have time for Q&A at the end. This image from Torsten, he shot with a webcam, not a webcam, but imaging source camera. That gives you an idea how long ago it was. Most people are using ZWO cameras today, whether video or mono. That's mostly what I see. It's interesting. And down here, we can see some very deep dips corresponding to these gaps up here. And that's the methane on these planets. So we're observing the atmospheres of these planets from the backyard. So, in 1881, Henry Draper, the catalog guy, imaged a comet. Hey, if Hank can do it, so can we. So here, you can look at the equipment down here, not much equipment. Even though this is an extended object with a star analyzer, we were able to see this little string of gems on the comet. And there are the emission lines from that comet. This was imaged by a guy named Vikrant Agnihotri in Rajasthan. And it's remarkable how much can be done. Now, even though this is an extended object, it has a compact enough core that we didn't need a slit to capture it. So here's a more recent object, comet. We again can see the sodium emission lines. And these are the kinds of references which, when you come across them for the first time with more time on your hands, you do some digging on the web and you understand a little bit more about their significance. So I love this slide. This is, again, a video camera with a star analyzer on the nose. But look at this. Anybody who uses a C-clamp as part of his equipment setup is my kind of guy. The problem is I would have tightened that C-clamp too much and it would have collapsed my camera body. This is a video camera. And what Robin was doing down here, you can see down here, that's on the left is the actual comet. And then over here is the spectrum of the comet. And it brightens right here because of an outburst. And here is the profile graph. And you can see the tentative identification. This is pretty nerdy. I mean, spectroscopy is a niche. This is a niche in a niche if you're looking for the spectra of comets. But some people do it and have a lot of fun at it. So I won't talk anything about the sun today. We've heard a lot about it a few years ago, and we'll again this year continue to hear a lot about it. There's some interesting spectroscopic stories we won't get into. Just a reminder that this term Doppler shift refers to the difference in pitch that a car has when it's coming towards or away from you. Again, if a car held its horn on and drove past you going quickly, you would hear go, right, high when it's coming towards you, low when it's moving away. And that's something we can use to measure the stars in a variety of ways. Suppose we were expecting this triplet right here. We knew from previous studies and from looking at things here on Earth, however, we knew that there were going to be 3 lines right here. But when we imaged a particular star, they were over here. That would mean that Doppler shift had moved them to the right and the object was moving away. And on the flip side, if they had been shifted in the other direction, then that would mean the object was coming towards us faster than stationary. So we can use this knowledge to study a supernova. Yes, I don't know if it's stupor or stupid, but that would refer to me in both cases. So the quickest exposition of a supernova on record is this, and that is you have 2 stars, and one is bigger than the other and dumps some of its gases on the small one, and it blows up. This is a particular type of supernova called a type 1A. There's other types, of course, and let's look at how we can spectroscopically study that. In M101, there was a supernova. It looked like that. And this is a video of what a supernova might look like. And notice the expanding shell. Again, just the explosive shell going outwards, because we're going to look at that in more detail in a moment. On the left here is what a supernova, actually not the particular one we're studying here, but what a supernova would look like. And again, you can see that explosive shell expanding away from it. So here is the star, and here's the spectrum that was captured by David Strange. You can see his equipment. Now we're getting a little higher end, right? He's doing some stacking, less than 15 minutes worth. But you can see some features in that spectrum. And it turns out that this big gap here is an indicator that we are looking at a type 1A supernova. So when we look at different types of supernovae, and this won't be on the quiz, type 1A supernovae, those 2 stars, have a very deep dip around 6,000. And you can see each different type of supernova has a different fingerprint spectrum. The cool thing about that is we can use that information to actually learn about that shell expanding. How fast is it coming towards us? Not a lot of math here, as you'll see in just a moment. Down here, David measured the wavelength of that dip at like 6150. In the lab, if you were to burn silicon, stationary silicon, it would be glowing at that temperature or at that color. That I didn't know the Doppler shift formula from high school. I couldn't remember it. Wikipedia is our friend. Even I could do a multiplication and a division and one subtraction. And when I plugged all those numbers in, just these numbers pretty much in the speed of light, we've now calculated this blue shift as that shell is coming towards us. It's pretty amazing that, I mean, there should be 2 wows there. One is that's really fast, and the second is I can't believe I was able to measure that in such a short, with such inexpensive equipment, and with a relatively short exposure time. So this is the kind of thing you can do. Now, Adam Rees in 2011 won his Nobel Prize for work he and his team did back before the turn of the century on basically the cosmological expansion. And he used, just as a reminder, he used these type 1A supernovae as standard candles. He actually had the opportunity, or I should say I had the pleasure of his reviewing some of my work in about 2010. He won the Nobel Prize later that year, I think, or in 2011. And if there's time later tonight and anybody asks, I'll tell that story. It's not particularly exciting, but what about the spectrum of a black hole? Well, of course, the black hole isn't emitting light, but the accretion disk is spiraling in and is very hot, so it's emitting light. So everybody knows, you know your skies pretty well. You know exactly where 3C273, the quasar black hole, is. It's in there, right? I couldn't find it, but David Hayworth of Portland, Oregon could. And you'll notice over here 2 little bright spots in its spectrum. Let's zoom in on those. There they are, those bright spots. And when we graph it, we get that intensity graph. This is the profile graph of a black hole, or the circumstellar accretion disk around a black hole. So this is sort of a cool story. Adam Schmidt was in his mid-20s in the 1960s. There's a wonderful transcript of the story I'm about to tell you. It's on my site on the samples page. And it reveals the person behind the discovery, which is what is so interesting to me. He did what any scientist does. He had unknown peaks here, and he tried to match them with a known. And what did he use? Well, he used the bomber lines. This is the screen I asked you to keep in your mind's eye when we were in my software. But he failed, right? Because he said, you know, if there was hydrogen here, I'd expect there would be something here corresponding to this known line. And same here, what peak would that be? And what about all these? Why aren't there lines? So he concluded first, whatever these are, they aren't hydrogen. But he was wrong, and he figured it out. They are hydrogen emission lines, massively shifted. Now, this is an observation that a lot of amateurs make. It's similar to that you need 10 or 20 minutes of integration time. But we are measuring the cosmological expansion due to the Doppler shift across 2 billion light years. It's pretty amazing that this light still has information, having come over that distance, that allows us to learn something about the object from which it came. So it's, the light has that information is astonishing. Human beings don't age quite as well. Here's Martin Schmidt a few years ago. So, this is before and after. He actually passed away a couple of years ago. I've been accused of throwing him under the bus with this little comparison. I'm just envious because he had a full head of hair there really late in life. So a couple more quick examples. If you're interested in doing mentoring or outreach with your equipment, these are the kinds of things that win science fairs. And this is just an example of an article I came across not long ago. So typically, high school students are going to have somebody like you mentoring them to accomplish these things. And it's really rewarding. And to be honest, I see more science fair prizes won by this than I think are deserved. This isn't that hard when you compare this to the kinds of life science projects that people are doing these days, kids are doing in schools. And by kids, I mean high school students. I think my explanation of that is, first of all, none of the judges know astronomy anymore. They're all life sciences people. So they don't really have a good way to judge this accomplishment, which is no small accomplishment. It might not be a science fair winning project, though. But the second thing is, I think that because they're giving away all these awards to the life sciences, they want to balance things out a little bit and bring in some of that classical astronomy. Anyway, that's my thinking. I don't know if it's true, but it is the case that you could use this to give back to your community. 2 more examples and then we're done. So far, we've been looking at, if I can find my pointer, there it is, at the hydrogen features, the hydrogen bomber lines. How deep is that dip? Or how wide is it? Excuse me. It's about 50 angstroms wide. Suppose we wanted to drill down and look at this. That's when we have to spend the money and gain the skills to use a slit spectrometer. So this dip is the same hydrogen alpha dip. Notice it's very sharp. And if we compare that to something that we know isn't moving towards or away from us very much, and that would be the moon, we can see the Doppler shift from the radial velocity of Vega. This takes a fairly high-end setup and the skills to actually capture data. Okay, I think this is the last example. And that is, let's see if I have a slide here. Yeah, I do. Suppose I need an example here. I need a star, basically. So I think this is a star, and it's rotating. This edge is coming towards you, so that light is a little bit blue shifted. This light is moving away from you, so that light is, the star is moving away from you, the light isn't. But so you have red and blue shift, which means the star is no longer the same color as it is when it's rotating quickly, it changes in color. This is what the absorption line looks like on a fast rotator compared to a slow rotator. Who would have thought that by just studying the color of a star coming out of a prism-like device, we could tell how fast it was rotating? Okay, so how do you get started? Just to finish up here, you need a star analyzer grating, which we sell. You need some sort of camera, almost any camera. You need some sort of data reduction software. My software is called RSpec for real-time spectroscopy. Works with FITS files, works with videos, whatever you've got. These are some shareware programs out there. They've improved over the years. They're still pretty tough to use. And you may need some spacers because this distance, while not critical like focusing, needs to be approximately optimal. There are tons of books out there. For those of you who've been doing this for 20 or 30 or 40 years, you've climbed some pretty steep learning curves over the years. This is not one, because we've got so much social media online and really good books out there. There are opportunities. I wanted to show you here just one of the books, which is a really excellent learning book. Here's an example of the spectrum of a Seyfert galaxy. I'll be quite honest, I have no idea what nitrogen is all about or what any of this is. But he is the author of that book. That's this book here, the Spectral Atlas. And so this becomes a book where you can basically, he explains what all these features are. It's a astrophysics book for us, basically. We've got a great forum. The AVSO, we were invited, and they hosted us at another SAS, the science conference down near LA that has just been discontinued in the last month or so after many years of serving our community so well. I gave a workshop there to about 100 AVSO members. It was this will date myself. It was videotaped, and probably was video back when I gave it in like 2012 or 13. And it's online, so you can download not only watch the video on YouTube, but you can download the sample data. And my software is free for 30 days. So you tomorrow literally could walk through with 2 screens, watch my workshop, do it on your screen with the sample data. And at the end of that, it would take a few hours. You'd really, in your gut, you'd really have a much better appreciation as to what this is all about. I've been just so fast going through it tonight. There are opportunities for pro-am collaboration. The AVSO has their own spectral database. There are spectral databases in Europe that also collect amateur data. To be frank, there aren't as many opportunities as we all would like. It's a peculiar situation because a professional basically has to feed a group of us to keep us going and to collect the data. And this is one of those projects that went very well. These are all amateurs here, except for Bob Stencil. And he's at the University of Denver. And they did some really great work. So again, just a reminder that the whole foundation of everything I talked about tonight is this HR diagram. And if you're familiar with it, great. And if you're not, this is a good opportunity for you to become familiar with it. There's Vega that we looked at in my software earlier. We saw Betelgeuse, and we saw some other stars over here. There's lots of opportunities for learning there. We've come a long way in the last 50 minutes. I appreciate you all sticking with me. We've also come a long way in the last several hundred years. There's Fraunhofer back, I don't know when he was, there we go, in the late 1700s or early 1800s with some of the first spectra. And there's that guy Kirchhoff, who I mentioned really briefly. So thank you so much for your attention. I hope that I entertained you, that you learned something. I'll be happy to answer any questions that come up now. This, as I mentioned, is where you'll find how little I do know. I'm very broad river, but I'm not very deep. You can see my contact information down here. I'm always happy. This is my passion. I just love helping people get started because I get a lot of thanks back, and because I feel really good about giving something that's so exciting to people who really appreciate it. So if you're one of them that want to take the next steps, I'll be there for you. Thanks again. I'll stop screen sharing for now, and I appreciate being invited to speak tonight. Thanks.
Okay, I'm sure you all have a question or two at least. There's a microphone there, and there's one right here. Help yourself. Jeff, go ahead.
Hi, thanks for the talk tonight. I have a couple questions. First one is, have you taken your black body radiation curves and compared them to the PROS curves and had some collaboration?
I don't know what the CROS curves are, but could you clarify what those are? I'm not sure I'll be able to address that part, but I'm curious.
So like I have gone on Google and found the black body radiation curve for a variety of stars. And so you can find them, you know, on Wikipedia or whatever. I was wondering if you've ever compared yours with theirs.
Absolutely. That's a really great question. I appreciate you thinking along those lines. I am going to share the screen just briefly, just to show my software. Give me a second here. There's my software. I'm going to pause this playback and just clear up my screen a little bit. So this curve should be representing the temperature of the star. Let's compare it, like you just asked. Let's compare our data to a professional library. That's what's built in on this screen. Now, I know it's one of the few star types I know off the top of my head that Vega is a type A star. So this is the temperature curve of a type A star. And notice that as we get into the blue and ultraviolet, it just keeps getting brighter and brighter. But our data doesn't. Our data crashes down. Why would that be? Well, of course, it's because our cameras aren't sensitive enough. They lose their sensitivity in this region and, of course, up in the red. So there's no match out of the gate between the Planck curve and the star curve. However, there are procedures, and by the way, a huge collection of tutorial videos in the product. They're on our website, and they're also here, and they're really a great learning tool. But there are procedures in the software to correct for this. And I won't get into how you do that, but I will mention something that's been interesting for me to learn, and that is, as amateurs, we can't use even the corrected shape of this curve to measure star temperature because we're only looking at this visual region here. Look at all that energy that's over there. We're just not seeing that as amateurs. So if we use, there's things like Wien's law and Stefan Boltzmann, there's all sorts of formulas to try and calculate star temperature from the shape of its curve. Even if we correct the curve, it's only going to be an approximate temperature, and sometimes it's going to be off considerably. That's probably a longer answer than you wanted, but it is a topic which is an interesting one to explore, and a lot of us still will do that correction, especially on higher end instruments, because it's important when we're doing quantitative work. Did that help, or did I miss the question?
Yeah, it did help. I don't know if you have like, if you could take a photograph, get a black body curve, or let me restate that. Take a slit, take some standard white, and get some kind of balancing so you can adjust the curves that you have to match some kind of datum balance.
Exactly right. I love it when people, arrive at the conclusion that I was going to present. It's much more fun for me if you do it. That's exactly what the procedure is in the software. We use that library of their standards. It could be a lamp in the lab, but we use stars, so the professionals have done all the hard work you described. So the curves that they give us that are in the software, in that reference library, are standards. And so basically you divide our data by their data and you get the QE curve of your camera. And then you can use that QE curve to correct all future spectra. That's exactly how you do it. Most of the work that gets done by professionals on star temperatures and stellar evolution doesn't use the general shape called the spectral energy distribution. Don't use that shape. They use actual features, absorption lines, emission lines, and that's how they determine stars' life history and story. But the shape is not unimportant, and so your question is a reasonable one to ask and show some insight into the difficulties that we have, because our cameras aren't really true sensors and truly accurate sensors. They just don't pick up enough of the red or the blue or ultraviolet photons. They get lost.
So also when you look at 3C273, it has an extreme redshift. Do you have any stars that have enough of a blue shift to redshift just from, interstellar galactic motions that you have to move your black body curves right or left to account for it?
Man, you're a great plant. I hope you'll come to the rest of my talks this year and ask the same questions. They're great questions. With the resolution of a star analyzer without a slit is too low to detect any movement of stars in our galaxy. The radial velocity just isn't high enough. Now, maybe there's, they've found recently these, I think they're in the Milky Way, these super high velocity stars that are getting ejected from the galaxy. And I don't know the orders of magnitude involved, but typically it takes higher end. A slit device can measure the radial velocities you're describing very easily. In fact, you can put a slit device on the rings of Saturn and see that one part of the rings is moving this way, and the other, the spectrum shows that the rings are moving around, and one part of the rings are coming towards you, and the other are moving away. You can actually see that Doppler shift. So, but it's a matter of just the accuracy and precision of the instrument as to whether that's something you can do as an amateur, and that requires a slit, as I said.
Can I throw one more question out?
Sure.
I'm sorry, I'm hogging the show, but I got questions. I know like with a hydrogen alpha filter on a scope, you have to have like an F30 scope where the light cone is coming at acute angles that kind of screws it up. Do you have to control like almost like a Code focus, had a really long F ratio to control your spectrum?
That's a great question too. I don't know a lot of optics theory. What I know is it's sort of at the other end where you run into trouble with a really fast telescope. That converging beam is too steep to work with a grating. So anything faster than F4 or so just isn't going to work, which is a bit of a bummer for me because Celestron's new Raza telescope is, I think it's F3.5 or F4. It also mechanically doesn't allow a grating to be inserted into it, just the way it's designed. And too slow a telescope, the problem is that the star is so big on the sensor that it just hides all the features in that profile graph. So there is on the site a calculator where we've seen these kinds of calculators for field of view calculators and things for other types of equipment issues. And this way you plug in your focal ratio and your pixel size, and it just shows you how's it going to work for you. It has some like stoplights, red and green stoplights that show you if you've got the grating mounted where it needs to be. This is a little bit of a speed bump getting started, is sort of determining where the grating should go in line, and is my camera and telescope matched for it. I quite often guys will just, and on the page I'm referring to with our calculator, it says just send me your equipment specs and I'll work through it and let you know what you need to use. Great questions though, thank you. Clearly you've been doing this for a long time and thought a lot about it, so thank you.
Thank you.
Any questions? You good, Debbie? So I'm about ready to buy a new DSLR, and I'm just curious if you have a preference for doing stuff like this, whether it's Canon, Nikon, which one?
I don't, but that's because I see a lot of guys doing it, and almost everybody's using Canons, but I couldn't tell you why. We do have a forum where I was going to say the community knows a lot more than I do, but a lot of individual members. It's not like the collective knowledge. A lot of members there are really well informed. You could ask that there. I don't think it matters much. And then there's two ways to do it with a DSLR. You can actually just put the grating, if you're not using a telescope, just put the grating right on the lens cap, where the lens cap goes, and we have an adapter for that. Or you can put the grating between the camera and a telescope. So we've got adapters on our site for all that. And again, I'm happy to work through that with you. It's a good question. It's reasonable for you to ask it. I wish I had a little bit more information. I don't think it matters appreciably. But because DSLRs aren't cooled, we don't need wide fields. So DSLRs in the long run, and this again, just sort of to end up on a sort of a draggy note, when you take the photons that normally hit our sensor without a grating, in a handful of pixels, and now you take some of that light and spread it out, you lose magnitude, a limiting magnitude. Your limiting magnitude when you put a grating in line drops by 5 or 6. I'm really sorry to say that, but the good news is there are so many bright stars that we never care about now, but with a grating they become interesting. That's not a big problem. But again, aperture matters and camera sensitivity matters. So get your DSLR for all sorts of great activities, and you will be able to capture spectra with it. But keeping in mind, it's not quite as sensitive as you might like. Other questions?
Next question would be, if you were trying to get the gradient or the spectroscopy of our own star, our sun, with a telescope, could you do it using a broad band filter in front of your scope? And then
I wish that were the case, but unfortunately, no. The problem with the sun is it's so big
Yeah,
that without a slit, it's just mush spectroscopically. The good news is we're having an eclipse in a few months.
yeah.
It's a rather short time period to get up to speed, but a lot of amateurs are going to put a star analyzer on the nose piece of a DSLR, zoom way in, and during the totality, they'll be able to actually get some really good spectra. It's a pretty cool activity to do. But if you have a slit, then you can do the sun with no problem and see all sorts of interesting spectra. I mean, I don't have a sample of it here, but there are thousands and thousands of lines that you can see with really simple gear. And some people dive into that and want to understand where all those lines are and label them. That's a good question. I wish there was a way to do the sun, because I think it would be a really great high school activity.
Well, that's the reason I was asking is because here this Saturday we're doing a STEM thing here at this Stockton County Office of Education, and
Yes.
if there's a way to do it, I'd love to be able to show that. But
Yeah, I wish there was a way
we
to
don't have
do
a
it.
sled.
Yeah, but stay tuned, because there are devices that do that, but they cost $500 to a couple $1,000s. Don't stay tuned expecting that I'm going to come out with something. That's just not a direction I plan to go.
One way I did it
Questions?
at school was I took a ball bearing, a chrome ball
Yes.
bearing, and I just did it with the reflection of the sun on the ball bearing.
Yes, that'll work, or even a stainless steel rod. And what were you using for a telescope? Was it a camera or a telescope you were using?
This is a class project. We're using eyeballs.
Oh, cool. Well, I mean, you can just you should experiment a little bit with it, because I think that a cell phone would be able to see the spectrum pretty clearly that was reflected off of BB, or like I said, a highly polished stainless steel rod. If you go that route, let me know, because I can point you towards the highly polished products that people have told me we should use. I've got a couple sitting at home, but living in Seattle, they just haven't gotten a lot of use, as you can imagine. What else? Any other questions?
So Tom, I've got a question. Unlike Jeff's, I'm going to go to the other end of the spectrum. No pun intended. You're going to have to dumb it down for me, though. So we're taking a picture with our digital camera, like a JPEG or a raw image, right? And we're just going to take that picture file and import it into your software.
Yep.
Okay.
Yes.
Is your software cloud-based, or is it residing on my laptop?
It's on your laptop. Yep.
Okay.
So back in my software here, I'm not going to spend a lot of time here because we're finishing up, but this open button lets you open FITs or bitmap or raw images, and they just show up here, and it's all on your machine.
Okay. I assume the higher the resolution, the better.
So
like a raw image be better than JPEG?
Pardon me?
Like a raw image would be better than a JPEG because it's higher.
Yes and no. For most of us at the level that we're at, including me, the high resolution doesn't really help a lot. And there's, again, if you have, if you've spread the light out across too many pixels, you've, challenged your signal to noise ratio. So that's the calculator on our site. One of the things that one puts in is what's your pixel size, what's your focal length, and what grading you're using. And it figures out and gives you a range of just how high a resolution you need. Now, if you're doing a lot of stacking, then the higher resolution is much more helpful, as well as, and by higher resolution, I mean, more pixels per inch or millimeter, but also, 64K, high resolution images are much better than 8-bit video images. But you'd be really surprised, I have been, is just how unimportant that is for most of what we do. That's one of the things that has been a big relief for me, is I didn't have to go real high end in terms of equipment. In fact, I don't even recommend people use raw images until they discover a need for it, which almost never comes. Just use JPEGs, they're smaller and faster. If you're doing a lot of stacking, that's a different thing, but you don't have to stack for what you'd be doing for years with this, depending on how good and how long you are at it. It's a good question. Well, where are you? Is this a school or where are you all?
We're at the County Office of Education here in Stockton, and we have use of a lab classroom.
Oh,
Yeah,
good.
so, Tom,
Well,
one
let's-
question. You mentioned that light pollution doesn't affect the quality or the readings, but that seems strange that any light that might come from a fluorescent or mercury vapor has a wavelength that might appear in the spectra or.
Yes. If we're doing quantitative spectroscopy, where we're measuring the depth and the full width half maximum of the features, then light pollution becomes something that begins to have an impact. But for the most part, all we're doing is going, oh, gee, look, there's a dip there. Look, that's titanium oxide on a cool star, or that's the emission line on a Wolf-Rayet star. So, yeah, I don't want to oversell the immunity to light pollution. In fact, I'm in Palm Springs right now, and I'd rather go out here. And I was out at the pool deck just before dark looking for power because I want to set a telescope up. And I'm hoping, I really don't want to drive out into the desert and have to have batteries and everything. And I think it's likely I'm going to be able to capture some decent, simple spectra here. But that's especially if you all are doing outreach with students, you'll be able to get some really useful data. I'll tell you just one lab, which it just depends. It sounds like you all are really doing some pretty cool outreach and working with educators and other people in your community. And I want to thank you for that and congratulate you. I know it's its own reward, and that's why you do it. That's why I do it, among other things, because it fills my heart. But as I mentioned earlier, chemistry teachers love this topic because whereas physics teachers don't have to teach it, they have so much to teach. Kinematics, everything. Chemistry teachers, what we're talking about tonight is really the foundation of chemistry. And so you get into a position as if you put together a presentation, and it might not be something you can do this year. It might take a year or two to get comfortable doing it. But one of the things that we've seen very popular is gas tubes, where you go into a classroom, and a lot of the professors have them or educators have them. You have glowing gas tubes and they're different colors, and the students use little handheld spectrometers. Well, you can use my software to show that, and then you can show the spectrum of a star. And it's really impactful, and the teachers love it because it's non-chemistry, but it's the same topic, and so the students get a lot more breadth and appreciation for what's going on. So if you're doing a lot of this outreach, don't worry about light pollution. You won't. Well, you don't want to do it on the football field while all the lights are on, but I think you'd be delighted at how easy it is. Anyway, other questions? I don't want to overstay my welcome.
Anybody else? Anyone on Zoom?
I have a couple.
Go ahead, Eric.
Couple quick questions. I've seen, I believe, a couple different versions of the star analyzer filter, one with a 100 and one with a 200, which I assume just means it has double the gratings. But is there any real benefit to one over the other?
Yeah. The 100 is how many lines per millimeter. And the 100 was all we had for 15 years or so. The 200 is less frequently used. It's not twice as good, but what it does is in certain circumstances, like with a filter wheel, you just can't get the grating far enough away to allow the light to spread out enough. So you use a 200 line per millimeter grating, which spreads the light out more quickly. And so it's it's more of a mechanical issue than anything else. Also, really big telescopes, like anything bigger than even perhaps a C11, but certainly, I mean, I know CDK-17s, plane waves, are using star analyzer gratings. Typically, when you have that much aperture, your star is so large on your sensor that, again, you can spread the light out more with the star analyzer 200. So there is a page on our site which lists, I think, 4 reasons. The other reason, just to give you the flavor for it, is filter wheels often have very small compartments. And the Star Analyzer 100 just won't fit into a lot of filter wheels. There's just not enough space. So the 200 is a shorter, thinner filter ring. And so it fits more easily. And so it's that kind of thing. Our calculator will recommend, it will say, you know, you need a 200. The 100 is not going to make it for you on this telescope. And that's the kind of thing which I'll shepherd people through with pleasure if you decide that you want to explore a little bit more about the possibility of doing this. It's a good question. I'm glad you've been looking around.
Thank you. And one more. Can your software help to analyze the specs of other astronomy filters?
Yeah, that's a good question. It's been done. Dennis DeChico did it and wrote an article in Sky and Telescope magazine, not with my software, but he did it, I think, probably 15, 20 years ago. You know, he's a really capable guy. It's not easy to do because there aren't any real standards in the lab for you to base your observations on. So you'd have to compare the filter and then remove the filter, and now you're dealing with a star. And so what's the star spectrum look like? There's a lot to it. So it would be interesting and a fun project, but frustrating because the best way to do it is on a lab bench. And they do it basically. All those graphs you see of the passbands of the filters that we buy are all basically spectral profiles that are being graphed by software like mine. So the real challenge is the optics and the standard lamps and all that. Processing in the software is the easy part for that particular project. It's a good question. I love that. This is really quite a group. You know, I always am a little nervous when I go into these Q&As, you know, whether it's just going to be dead. But you guys, I'd say guys, I haven't seen any women in your group, but
We got one over here.
Oh, good. Well, welcome. Sorry I didn't see you. Sometimes I like try and zoom my screen in and see people, you know, and call out like, hello, person wearing the red sweater. But anyway, I can't see very well here on my laptop anyway.
Okay, any other questions or for Tom, either on Zoom or here in the room? Excellent presentation, Tom. Again, we thank you very much. Enjoyed it very much.
Thanks so much. Have a good evening, everybody. Thanks, James. Thanks, everybody.
Thank you. And just a reminder, I know he went through a lot of information fast. And for me, I'm going to go back and watch the YouTube video because Eric, like a few days, Eric has the YouTube up on our channel. So I think I might slow Tom's voice speed down a little bit so I can understand it. Okay, so Eric, if you'll switch to the announcement slides. And meanwhile, last call for Jerry's fantastic chocolate peanut butter cookies there. So, thank you, Jerry, for bringing those tonight. And thank you all for signed up for the future refreshments. Appreciate that. Okay, so published in the newsletter were the entire star parties and public outreach meetings for the whole year. So you can see that in the newsletter. So here we've captured just February and March events. So this Saturday is right here at San Joaquin County Office of Ed. Who's coming out? Okay.
Actually, we need to talk about what time. Early shift, late shift.
Well, Doug, this is your time to
Right.
speak now or forever.
So who needs to do, well, early we need to have the solar telescopes out there.
I have both of them.
So you got, he's gonna be here early. Anyone else need to do the early shift?
I need to be early because I need to get out of here by
Okay.
about 12:30.
All right, Michael wanted to be here, like.
Mike Chapman.
Mike Chapman also.
Okay, so there's three of us.
Right, Omar was talking about just texting me because he can do 10 o'clock also. We got more volunteers than I think we need, but
Good.
then that means that I'll come in the afternoon. Who else can do the afternoon? Okay, so we three.
What does the afternoon mean? 12:01 p.m.,
Well, 10 to
Tell
1
them.
and then 1 to 4. I would say.
1 to 4. Okay.
So I actually found this map from their website
Yeah,
where they actually have us listed inside SAS table and outside over by the deli. So this is on the right-hand side here is the front of the building, the back of the building on the left. Here's our current room right now, Harmony Grove. But that's about here's the front lobby. So this is about where we're gonna be. They showed us.
I couldn't see your hand when you covered over it. Are we in red square?
Yeah.
Yeah.
Yes, right here on the outside,
Oh.
down here on the bottom right.
There.
Yeah,
Oh, gosh. Oh, wait a minute.
there's
That thing
this,
should be illegal.
it looks like there's
Probably is.
it looks like there's a partition here, but last year I don't remember there being a partition. It was just one big room, but they might have it up. I don't know.
Right.
All right, so like I said, I'll be out there at 1 then. I brought,
Hey, Eric, switch back to that slide. Let me point something out.
Okay.
You guys know that the fundamental thing that's going on here Saturday is the school science projects. They got graded and then they advance to the next level, show up here. So if you get here early or stay late, go to this room. Because you see all the fantastic work the kids have done in their science projects. It's just so interesting to see what they're doing.
That's all along this. You walk down that way, it's all along that left wall.
Yeah. So, okay,
so
thank
I've
you.
got some bookmarks here. What, we got, 1, 2, I got 300 here and I got 2,000 in the car. So morning shift, you guys.
Okay. Okay, so we've got bookmarks. I got striking sparks handouts.
Right.
What other collateral material do we have?
Oh, I've got the banner for way down on a table, tape it down so that you can.
Okay.
It says Stockton Astronomical Society.
Okay.
Um,
Very good. Okay, Saturday's also high altitude star party. Jeff, what's your crystal ball forecast tell you for the weather on Saturday night?
I don't know. It's gonna probably suck, but I don't know.
It's
Every
not
time,
gonna
every
be-
day. I
You're
look at
making
this-
lousy meteorologist.
Every day I look at this thing, it's got the cloudy thing and the sunny days and they just keep changing on me, so I don't know.
Okay. We'll look for your post on the Yahoo group
Can do.
and the Google group.
Why didn't you just check Magic 8 Ball?
Yeah.
There's, they had quite a bit of snow.
I don't think they really work.
Yeah,
Yeah,
they had quite a bit of snow. You might not even be able
Yeah.
to use in that field for it.
even at the health one.
Yeah,
Yeah,
Well, there's always Highway 4.
yeah.
Yep.
snow level was 30, was right at 3,000.
What is?
The snow level.
Oh,
That was
wow.
last one.
Well, Highway 4 is 1,100 and Hellport's $4,000.
Right.
So,
Okay, and then next week on Friday is at Delta College.
I've got to email into the outset to make absolutely sure.
We'll confirm that.
So once again, depending on weather, if you can help out on that one. Anyone, Bill? Peter? I will not be there. I'm gonna be leaving on Thursday, so Bill needs some help out there, at Delta. So I'm gonna have Yatsik, and you talk, and same thing with Saturday.
Mhm.
Starting in the park, I will not be here.
Out at Oak Grove.
at this moment, underground weather says Friday partially cloudy, Saturday sunny, Sunday partially cloudy. So at this moment, Saturday's supposed to be good.
Yeah.
Okay. So then that takes us then to the following week, then we're back at another STEM event. This is kind of a cool one. Bill, you went there last year to Lodi High School, right?
Yeah, Eric and I,
Yeah. Okay,
yeah, the sun was off.
yeah. And will we try to do both the indoor and outdoor displays or that just,
All up.
that's just with the solar scopes?
There's the
Okay.
advertisement for that one.
Oh, good.
10 to 3.
Very good.
I do have, a request for the 22nd as well, so calling all scopes, the 22nd, we have a opportunity with the Star Lab and everything, STEAM event. It's right across town here up Alpine on the other side of I-5.
Oh, Commodore Skill School?
Yeah. And, he says it's got more than 200 people coming, so. And it's only an hour and a half. It's a real quick one. So,
It's also like right next to the full moon.
yeah, it is, right.
And
The full moon
it's
is
also
2 days
this-
later.
Yeah,
You said it's on the 22nd.
22nd.
That's a Thursday?
Yeah. So if there is anybody interested, please contact Doug or myself.
so I can, if we're gonna, if you can get another person, I can jump in and help on that.
Okay.
I just did a quick check on stuff from NOAA, and the long range forecast for Saturday, the 17th, astronomy in the park is 45% chance of rain. Cloudy.
Anything longer than 48 hours, might as well use the magic 8 ball.
I understand, but I'm just letting you guys know that it's not looking.
It's a little too early to cancel.
The whole week before that, it's completely overcast.
Thank you, Father Time.
Those horns coming out of your head, James.
Pardon?
I said, I love the horns coming out of your head.
Okay, then a star party in Tracy at North School on the 29th. So, then we go, pardon me?
We have to be there at
Yeah.
what time?
Ah, Fred. I don't
5.
have that. Yeah, like 5 o'clock. That's 6 o'clock. So, yeah, we have a really short window.
You wanted to be ready at
Yeah.
5:30 or something.
All right.
Oh, is that right?
Yeah.
Okay.
Which, we're not gonna have much to look at 5:30, but
Okay. And then go to March, we have our regular star parties and meetings coming up again, so. Okay, you all know to contact Doug and or Bill Lytle. Bill's helping Doug now with public outreach. We have just such a tremendous amount of interest in public outreach and programs that takes 2 guys to handle it, so. Look for all your volunteers to come out.
either that or between Bill and I, we have half a brain, so,
The 2 of them make a whole, yeah.
no.
So the two of them make a
Okay. We've got some more opportunities to volunteer, to get involved, in different club activities. So next slide, Eric. This is one, we have gone through months and months of working to get the admin rights and the access to our social media accounts straightened out, and we're there. Thank you, Eric. Thank you, John Shemp, Jason as well, Jason Keys. So now we need a volunteer, a member, hopefully, to post routinely to Facebook and Instagram. The things that like our typical star parties, our club events, just a post on Facebook, just an announcement, date and time, location, that kind of thing. So keep it in mind, if anybody's interested in doing that, we'll try to make you the easy task to do, but we would like to have somebody designated that does those posts, not just random hit or miss members. So I'm looking at all of you, and I know you all have a right arm or left arm to raise in the air. So think about it, or think of somebody to suggest. Yes, thank you, Jeff. Okay, get a hold of me. And the next slide, Eric, we have another public outreach. Y'all remember in 2019, a bunch of us went to Glacier Point in Yosemite. Some of us even got through the traffic and got our telescopes set up. Eric, I know you had such a bad experience. He like waited in traffic for like 3 hours. And then when he got there, there was not a parking place. Hopefully, Lassen Park, they've reached out to us and the Sacramento Club to do these different events this coming spring and summer. Starting off with a star party March 9th. I know that's fairly soon. And then they want to have 2 staff training days. These are during the daytime. Evidently, they have some telescope equipment, and they just want to teach their rangers, their naturalists, the basics of how to operate the telescopes, and not teach them the night sky or anything, but just the fundamentals, how to run a Dob and point it at an object in the sky. So the 13th of April or May 18th are the dates they've earmarked for the training. And then they're planning kind of a big star party July 27th. So if you guys are looking for something to do this summer, this would be a fun one to go to. Bortle 2 skies, so super dark. If you go and you're a volunteer, you get free admission to the park. That's $30 right there. You get lodging. It's probably a campground they'll give us. I don't think they're going to give us a dorm room or a cabin, but probably a free campsite. So it'll be a fun time. Great viewing, tons of visitors that are really interesting and fun to observe with. So keep those dates in mind. Reach out to me if you're interested in any of these. And for you all that don't remember where Lassen National Park is, it's about a little less than 4-hour drive. I think it's like a little less than 300 miles. Go to Redding and turn east. Great place, and the weather should be really nice in July. Yeah, Jeff.
Is the star party going to be in the parking lot at the trailhead for the summit?
I'm not quite sure. I believe it's at the visitor center at the south entrance to the park. Does that make sense?
I haven't been there for a long time. They used to have them in the parking lot right at the trailhead for the summit, and it's dark there. I mean,
I've heard these were
really
big
nice.
events. Yeah, and they're after from COVID, they stopped them, and now they're looking to bring them back on. Chico State's up there with their physics department and their astronomy club, and obviously the Sacramento club. So it should be a really, really good fun time. Doug's working with, hopefully we'll hear back from Yosemite National Park.
Jill, we have I tentatively said that we have people interested in doing Glacier Point again. I sent her an email, and we would work with the Fresno group again. They've agreed, but I haven't heard anything from her. I told her that we would like a little bit better. We need to do something about the parking. That we need some designated spots for us to park.
Yeah.
I told her that camping, it would be better if they could put us in the horse camping area. So we have a big area that we can.
And it smells better there too, right?
That way nobody notices that I didn't shower. But it was just, we'd have more room.
Yeah.
And told her to be, if we can get some help bringing equipment in, that was one of the things. So those are a couple of issues that I brought up. But it was a spectacular.
It was spectacular. The viewing from Glacier Point with Half Dome in the valley off to the east, it's just amazing. Amazing.
The crowd was fantastic. We went till, I think we were there until like 2 a.m. with people still looking at telescopes.
Yeah.
And there were.
I thought they only went like 10 or so at night, and then the rest of the evening was supposed to be our free time to observe for us.
There were people there
that
until
was like
like 2 in the morning, or 3 in the morning, something like that. Yeah. It was, but it was really good.
Yeah.
It was excellent.
So a lot of good opportunities for going to some really cool places for viewing this summer. Okay, Eric, next one, please. So the executive committee has worked on, and we want to expand this because of the interest that we're seeing in astrophotography in the club. So we want to open up the newsletter to contributing members to share their photographs. So Mark Gibbons is volunteered. You know how we get people to volunteer? We just get them to We get them to make a suggestion, and that means he volunteered. Yeah. Thank you. So it's really simple. If you have a photograph, whether it's a deep sky image or just something like an interesting landscape with the night sky, or you see here this sample here, it was the Milky Way at Pedlar Hill that I took on my my DSLR. Just submit that to Mark. Here's his email address. And if you don't remember his email address, it's in the masthead of the newsletter. Mark M. Gibbons at stocktonastro.org. Send him your photograph with your name, the name of your photo, the location and date, whatever gear you used, and any other specifics. Mark, can you think of anything else that they should provide you at that time? Or
well, in the camera gear, it'd be good to have the telescope that was used. You can include as much as you'd like.
Yeah, the exposures, durations, and the stuff like that. So,
right.
Yeah. Yeah. So, looking forward to some of your photographs appearing in the newsletter. I mean, we got a bunch of them for the eclipse in October. A bunch of you took great pictures, and we all shared them on email and stuff. We could post them to social media, and we'll put them in the newsletter. So I think that's it. Is there another slide, Eric, or is that the last one?
I think there's one more. I think.
Yeah, forgot the most important one now. So another thing the executive board has been talking about doing is putting together some group outings where we all just get together, carpool over to a site, and go to a program. And so these 4 kind of floated to the top, but this doesn't have to be our list. So I wanted to, by a show of hands and on Zoom, kind of vote for your what might be interesting to you. I'm going to go through them in just a moment. And I didn't ask you before, but Jerry, do you have a pencil and paper? Can you kind of jot down whoever raises their hand, the polling? Could you record that for me, please?
Okay, so we have Chabot.
Yeah, so Chabot over in Oakland has a great facility where there's exhibits, there's telescopes, there's observatories, they have planetarium programs, just a whole bunch of things. Once we decide that that's where we want to go, or we're going to have a group, then we'll decide on exactly the date and the time, the type of program that they offer. Maybe they can tailor something to just our group, so it's a private event. So yeah, Jeff.
On Friday nights at Chabot, they have their telescope making workshop, and Eric and myself and Mike and Ronnie and Bill went over there on a Friday night. And we got to go through their telescope workshop, and then they gave us a tour of the observatory.
Very good.
So that Friday night might be the magic night for that.
Yeah. So then the Mosaic in Sacramento, y'all have driven by the Museum of Science and Curiosity in Sacramento. They have a dome theater, lots of other exhibits that aren't astronomy related, but science and related nonetheless. They have astronomy related theater programs in there, and that's nearby. Lick Observatory. Bob and I were talking about that. This would be a great place to go to see the historic telescope. They have viewings and observing. Bill, you've been there before, right? You've observed from Mount Hamilton. Yeah, both of you guys.
Yeah. He's just at the foot of the mountain.
Yeah. Little bit more of a drive, but if we're carpooling, it might be fun. And then lastly, I found out that the new planetarium at Sac State in their science building is doing public programs, planetarium shows and theater shows. So book for one or book for as many times as you want. So let's start at the top by a show of hands. Who's interested in going to Chabot? Keep them up until Jared.
I'm on all of them.
Yeah.
Everyone. Okay, everyone.
Okay. How about Mosaic in Sacramento? Who's interested in going up there? I'll go. Yep.
Got one online, right?
Yep.
And then Lick Observatory at Mount Hamilton. That sounds like a fun one. Yeah, that's kind of unanimous there. James, you got to vote. You got to come out with us.
I did on the last one, but
Voted on two.
Okay, great. Great. Okay, and then Sac State, their planetarium. Who'd like to go up and see that? I think that might be interesting as well. That's run by their physics department.
And you said that was open to the public?
They have public programs scheduled, yeah.
So you can just ask if it's open to the public.
Really?
That's-
Oh.
Planetarium?
Uh-huh.
No soup for you.
Oh, you didn't see the sign outside that said old white men only?
No.
And then the
Okay.
fifth one is Vegas. Vegas, anyone?
Yeah.
Yeah.
Yeah, and if you guys think of someplace else, within driving distance, that we could go to or an event, please let us know. Think about putting together something for this spring and this summer, a group outing. So, Dennis?
I have a suggestion.
Yeah.
I haven't been in ages to Lawrence Hall of Science. I think they used to have a planetarium there, small one.
Yeah.
Lawrence Hall of Science. Where's that?
We're going to park.
The top of the hill behind.
San Francisco, yeah.
Oh, okay.
There's also.
No, Lawrence is in Berkeley, Morrison Planetarium, it's in, it's actually Golden Gate Park.
Lawrence is at the top of the hill in Berkeley.
Right.
So let me hit up their website and see if they have programs. Yeah, thanks for suggesting that.
Yeah, that's a major
Kids. I used to buy with interactive. And you guys used to have their meetings down, I used to take my kid, let them go through it. And
Oh, okay.
all sorts of things they can, well, they had a lot of old Apple shoes and.
Oh, yeah, the vintage stuff, huh?
Yeah, Lawrence Hall of Science, it's still like, the Exploratorium.
Oh, okay.
FYI, we gotta close this down pretty soon. It's 8:10.
Yeah, and we're right at time now. So I think that's the end of our announcements and slides. And so again, I want to thank Jerry for the refreshments, Eric for all the AV. Thank you for disconnecting his power, Jeff. Thank you all.
To Tom, I don't know if he understood that we were out of power. He might have just thought we were talking and jabbering over.
Yeah, there was a little confusion. So.
I couldn't see to mute. Well, I couldn't see where to go to mute.
Uh-huh.
This is the hook. If we have someone who's really bad, just tell me.
Well, I wrote a note to Jeff, I said, anyone could have done something like that except for me, because I'm sitting here, my feet don't reach the floor.
So, excellent. Well, good meeting. I appreciate
did on the flight
everybody
from here.
coming out. And if there's any other comments or anybody would like to contribute? Yeah, Jeff?
Do we have a program for May?
Yeah, I'm talking on astrophotography.
Okay. How about June?
No, yes, do.
I think we're open June.
Yeah.
That's the first
That
month.
might be our first opportunity to have everybody bring their eclipse pictures and have show and tell on that.
Oh, that's a good idea.
Just a thought. Yeah, just a thought.
Okay. And you recall that you're the March program.
I am, and I'll be doing it from Port Angeles, Washington.
Okay, we were wondering he's going to be virtual. Hope there's nothing else then.
If anybody else wants to share that with me, please let me know. It's on the eclipse, so if anybody wants to share this with me, let me know, I'll let you in.
Right, the preparation with the kind of observing you can do at an eclipse,
Yeah, I'm just kind of doing like what I did with the October thing, only for tailored to this eclipse and the specialty of that, but if anybody who wants to talk about the eclipse, let me know, we'll just make a group thing out.
okay, I'll format that in an announcement coming out, so. Okay, is there anything else? Okay, we've got to be out of here in a few minutes, so thank you all and really enjoyed it, so.
But good night, everyone.
Good night. Thank you.
Great old horn one. Here is the census.
Thank you so much. This is